I'm Anil Kumar. Welcome to my series on Binomial Theorem. We'll extend the Binomial Theorem now in this particular video. We'll actually consider negative values of n also. That means all integers, right? I hope you remember that in Binomial Theorem, when we want to expand a plus b to the power of n, we could write in short form as sigma of r going from 0 to n of n choose r a to the power of n minus r times b to the power of n. In this particular case, the value of r is always between 0 and n, both included, and n is non-negative integers 0, 1, 2, 3, and all. Correct? That is what it is. Now, the basic reason why n is non-negative integer, can you tell me why? So the question here is, why in this particular case, why n is non-negative integer? Think about it. Well, the reason is right there before you. Since we want to evaluate NCR, and that is n factorial divided by n minus r factorial and r factorial. And so the reason is that n factorial is only valid for n which is greater than equal to 0. Similarly, r factorial is only valid for r which is greater than equal to 0. You get the idea. Since both n and r, because we are using this factorial and it boils down to that, we cannot use a negative number. And that is the major reason. So, what can we do? Well, if we kind of rearrange and take care of at least one part of it, that is, we could avoid n factorial some way or the other. In that case, we could actually use this particular expansion for integers which are also negative. You get my point, correct? That is what we are going to do in this particular video. So once we do it, we'll actually write NCR in a different way as given here, and we'll also show you this is the way it should be written to take care of negative values of n, and then as you see here, minus 1 to the power of r will be written as minus 1 choose r, and then we'll have similar more expressions to work with, right? Just as we were working with the binomial coefficients earlier. So similar questions with similar kinds of rules can now work when n is a negative integer. So that is what we are going to do. I hope you will find it interesting. Okay, so let's begin first by working on the binomial theorem itself, which we are used to, right? A plus b to the power of n is basically sigma of n choose r, a to the power of n minus r times b to the power of r, where r is between 0 and n, both included, and n is from 0, 1, 2, 3, and so on. N choose r is basically n factorial over n minus r factorial times r factorial. That is how you define it. Correct. Now, n factorial is defined for non-negative integers, and that is our restriction. Do you see the restriction? So I'll call this as a restriction. So the idea is to avoid n factorial. How are we going to do it? So basically, we need to look into this particular factor, which is NCR itself. So let's work on NCR. So n choose r, which I say NCR many times in short form, n factorial means n times n minus 1 times n minus 2 and so on. So in between we could have a term like n minus r plus 1, n minus r minus 1 and so on till 1, correct? All natural numbers when multiplied till n is what n factorial is. And in the denominator, we have n minus r factorial. So n minus r factorial can be written as n minus r times n minus r minus 1 and so on till 1, correct? And r factorial is written here as, let me shade it differently, as 1, 2, 3, 4 till r, correct? So both the factorial terms are currently written here, right? Up to R. Now, why did we write our tops out only up to, we had a middle term here, do you see that? N minus R plus 1 times N minus R minus 1, just to show you that N minus R factorial, when you expand, it begins with N minus R, and then what do you have? N minus R minus 1, correct? And then we have 2, 3, and so on, right? So that gives you an idea that we have something here in the numerator which can cancel away, correct? Okay. Now, clearly, what we have here is that we could cancel these terms in the numerator and denominator. So these terms will cancel away, right? So from n minus r minus 1 factorial, these terms will cancel away. And what we are remaining with is n minus r plus 1. So now this NCR can be written as n times n minus r times n minus 2 till n minus r plus 1 divided by 1 times 2 times 3 times r. Do you see that? So now we have NCR without n factorial. You get the idea. So we could actually expand the binomial a plus b to the power of n in this form using the method here, right? So I hope you remember earlier also, if you want to calculate what is 8C3 list, right? So we know what is 8C3, 8 times 7 times 6 divided by 3 times 2 times 1, correct? That is what it boils down to. Perfect. So clearly, we do not have a factorial term. So the last term here is definitely 8 minus 3. Do you see what 6 is? 6 is 8 minus 3 plus 1. 8 minus 3 is 5, and that gives you 6. Do you get the idea? So you can correlate with this particular formula, which we just derived, just in case you have a doubt about it, correct? So we did this kind of manipulation earlier, and we find that we could use this term 8 choose 3 without the factorial, and that's what we did here. Perfect. So now we could actually expand the binomial a plus b to the power of n as a to the power of n plus n times a to the power of n minus 1b. Increase the powers of b and decrease the powers of a, right? Both the indexes, when added together, will always give you n. But now see, the next term here, I'm not writing nc2, but I'm writing n times n minus 1 over 2, which is same as nc2, right? Similarly, we could now expand, and that becomes the general term of our NCR, correct? That becomes the general term, and definitely the series will move on till b to the power of n. So what you get here is binomial expansion where we do not have the n factorial term, and that gives you the idea. Perfect. So this is an equivalent form of the theorem where we do not have the n factorial term, correct? So it can be extended for all integers of n. That is critical for us to understand. Also note that n can be less than r. Now if I make n as negative, in that case, even this will interchange. N could be less than r, right? So we actually call this as the general form of binomial theorem, right? Sometimes we just call this as our binomial theorem, correct? So in general, if we now refer to binomial theorem, we'll take care of integers, n being integers, and n could be less than r. You get the idea, right? So that is how we kind of changed it now. Okay, now in another playlist, you'll find videos where we'll also consider the rational exponents, especially when we are expanding 1 plus x where x is less than 1. So we could have many other series, in which case we could also work with radical exponents. Okay, now we have another expression of this, and we'll now look into it in a different way. So let's try to analyze the situation further. So what we just realized is that now we could write NCR, right? And n could be less than 0, and n belongs to integers. Is that clear to you, right? So let's summarize. So NCR in general for us is n times n minus 1 times n minus 2 till n minus r plus 1 divided by r factorial, which is 1 times 2 times 3 times R. Correct? That's the formula which we just got. And now what are we going to do? We're going to substitute n with minus n. That is the whole objective, correct? So we are substituting this with minus n, which you see there, and all these terms will come with this negative n. Do you get the idea? So n is being replaced by minus n in the standard NCR and choose R formula. So once you do that, you get so many n's, right? How many of them? R of them. Perfect. And therefore, those negative numbers can be taken out as common, and we can write them as minus 1 to the power of r. Once you do that, everything in the brackets becomes positive. We have taken the negative 1 outside the bracket, and we written that as 1 minus r to the 1 minus 1 to the power of r. And so all these terms, the n and r, becomes positive, and so you get this particular expression, which is n times n plus 1 times n plus 2 till n plus r minus 1 divided by 1, 2, 3 and r factorial. Now that part could be written as n plus r minus 1, choose R. Do you see that? So that is how you could actually now connect this. So this can be written as in the combination form. So that becomes the formula for NCR now. So we can now remember that if we are talking about the minus NCR, then it is equals to minus 1 to the power of R times what? Let me write here n plus r minus 1 to r. Do you see that? So this series goes like in this direction. Perfect. That number is bigger than the others, right? We did the negative, of course, that will be correct. So that is how we get a new formula. So now let us try to work with some real values of n, which are integers, and see what values do we get as our answer. Okay, so here is some examples for you, right? So we'll just, here's an example for you. Let's try to figure out some values. So we have taken here minus 3, 5. So I'd like you to pause the video, apply this formula, and calculate the value for minus 3, 5. So when you put minus 3, you get an expression which is shown here. Do you see that? So we just use minus 3, 5 in our formula. Once you do that, what do you get? So we actually started with the first principle, that is, on the basic formula, we are redoing the whole thing. We are not using the end result. Look at it, right? So in the original formula, which was NCR formula, right, we have substituted minus 3. So we have 5 terms here, which will be minus 3, minus 4, minus 5, minus 6, right, till minus 7. So this is kind of like this: minus 3 times, minus 4 times, minus 5 times, minus 6, right? We need 5 of them. 1, 2, 3, 4, and minus 7 divided by 1 times, 2 times, 3 times, 4 times, 5. That is what you're going to get. Now clearly, so this is what you get here, right? Okay, so we introduced you few more steps in between so that you understand that we are not jumping on to this directly, correct? We're basically using this particular formula in getting to our result. Now clearly, minus 1 times minus 1 times minus 1 to the power of 5 basically is common. And so we took this as a common factor. Inside, we have 3, 4, 5, 6, 7 over 1, 2, 3, 4, 5. Correct? Now you know you could write this as 7 factorial over 2 factorial times 5 factorial. Correct? So this is how you could write this, right? 7 till 3, 2 factorial, we could write, right? So we could write this as, we could actually, let's add 2 more steps here. Okay. So what I will do here is, if I multiply and divide by 2 factorial, let us see. If I multiply and divide by 2 factorial, then what do we get on the top? We get 7 factorial on the top, correct? 7, 6, 5, 4, 3, 2, 1. And so we get 7 factorial on the top, and the denominator will be definitely 5 factorial times 2 factorial, correct? And that is what we got here. So we could write this as minus 1 to the power of 5 over 7 factorial divided by 2 factorial times 5 factorial. And that is what? 7 choose 5. You get the idea. This is 7 choose 5. Perfect. And so we could actually also get back to the normal way of writing the formula for n choose r. You get the idea, right? Now, this is a very, very important exercise. You see how we have written minus n choose r as minus 1 to the power of r, and this is the general formula. N plus r minus 1 choose r is the formula here, correct? That is how it works, correct? You can actually verify that if I substitute n as 3 and r as 5, it really works with this particular formula, correct? So that is what you're supposed to do. So we have shown that minus 3 choose 5 is basically equals to, in this particular case, minus 1, of course, to the power of 5, since this is a negative product. Result 7. And 7 you basically get with n plus r minus 1. So n plus r minus 1 is 3 plus 5 minus 1. Do you see that? 3 plus 5 minus 1 is what n plus r minus 1 is over 5. Correct? So let me rewrite this here just to use the space properly. So we get this as 3 plus 5, which is 8, minus 1 is 7, and you could use the formula and get the result directly also, as may be required in many questions. So that becomes a standard formula for you, correct? So remember to use this particular formula if required to solve many questions, especially when a negative integer is being used for n. Now let's take examples now to really understand what we have done so far. So I'll take up 4 examples. Example number 1 here is evaluate 2 choose r, right? Where r is from 0, 1, 2, 3, and 4. So we have taken values of r which are even less than n, you can see, right, in this case. So that is what it is. So it has changed the whole scenario. We are keeping r positive. Remember, the value of r should be equal to 0, 1, 2, 3, and all, right? So for r, we are not taking negative values. However, we're saying that n now belongs to integers, right? So this is what we are trying to say now. Okay, so the very first case, we're substituting r as 0 in our formula. And so we have r equals to 0, which is 2 choose 0. Well, whenever you have anything choose 0, there's always one option. And so the result is 1. So remember this part. So we are just using the common formula, which is always whenever. So there are no two ways about it. Whenever we have n choose 0, it is always equal to 1. Correct? Even, n choose n is also equals to 1. Correct? So there are no denying on this fact. Okay. Now, when we have r equals to 1, then we are writing this as 2 choose 1. And 2 choose 1, well, basically means what? Well, you could write this as 2 over 1, which is equals to 2. Perfect, right? So we get the value of 2. Now, for r equals to 2, we have 2 choose 2. So 2 choose 2 is 2 times 1 divided by 1 times 2. And that calculates to 1. But when we have r equals to 3, in that case, what do we get? Well, in that case, we have decreasing powers of 2, right? Decreasing numbers, consecutive numbers from 2. 2, 1, 0. 0 gets a multiple there in the numerator. Denominator is 1, 2, 3. And so the result will be 0. So thereafter, even when r is greater than 4, the result will be of 2c r will be equal to 0, right? So for any value greater than 4, you can see that if it is greater than the difference 2 in this particular case, right, then the result is going to be 0. Perfect. Now let's take another example. So I hope you have understood how we have applied the new learned formula, correct? Example 2. So in this example 2, I'd like you to pause the video, read the question, and then answer. We need to evaluate minus 1r for different values of r. And let's see what do we get. Well, for r equals to 0 as expected, we have got the value of 1. And what happens when r is 1? Well, it is this value minus 1, which you are going to get whenever r is 1, right? Perfect. So remember the fact that n choose 1 is always equals to n, correct? And n choose 0 is always equal to 1. So remember that part. Now next one here is r is equals to 2. So when r is equals to 2, we are beginning with minus 1. So minus 1 times minus 2, and in the denominator we have 1 times 2. Now they cancel, but sign also multiply and give you positive. However, I have purposely written this as minus 1 square, right? Of course, this is positive, and we get positive 1 as the result. Now, the next one is r equals to 3. That means it will be minus 1 times minus 2 times minus 3 in the numerator, 1, 2, 3 in the denominator. Numbers cancel as far as the sign is concerned, minus 1 cube, which is negative 1. And then when we do r equals to 4, minus 1 to the power of 4 will be the answer, which is positive 1. So in this particular series, you see what do we get? We get alternate positive and negative ones, right? So we get alternate positive and negative 1. So that is going to be the result in such cases, right? Very important case to understand from examination point of view. Now let's take example 3, which is similar to what we have done, but again we'll summarize some of our learnings. So we are now focusing on NCR, where n could be less than 0, right? It is now an integer. Okay, so in this particular example, we are taking n as less than 0. So NCR, as you know, the formula is n times n minus 1 times n minus 2 till n minus r plus 1 divided by r factorial. And if I substitute minus n, that is how the expression changes. You can always take minus 1 common. Everything in those brackets reverses the sign. So we get n plus 1, n plus 2, and so on till n plus r minus 1. And the remainder, I mean the divisor or the denominator is r factorial. Example 3 for you is evaluate minus 3r for different values of r. So similar to the previous two examples, again, we'll not try to change the values of r, keeping n constant as minus 3. And see, when we slide the values of r through different numbers from 0 to 4, in this particular case, what really happens to the value of the coefficients? Okay, so when r is 0, we know the result is 1. When r is 1, the result is minus 3. Now, let's take the case when r is 2. That means minus 3 times minus 4 divided by 1 times 2. When you simplify this, there are two negatives. So minus 1 square, and then numerator is 3 times 4, denominator 1 times 2, reduces to 6. When r is 3, we know there are three negative terms. So we get minus 3 to cube, right, as the multiplier. So a negative number is expected as a result. We have to multiply 3, 4, and 5 in the numerator, divide by 1, 2, and 3 to get the result, which is minus 10. Now for r equals to 4, what we get? So we'll now take minus 1 to the power of 4, right, and 3, 4, 5, 6 in the numerator, 1, 2, 3, 4, denominator, positive 15 this time. So definitely you get alternate positive and negative terms whenever you work with these series. Perfect. That's one thing. Second thing is, always you can calculate the value using the new formula or the new way of writing the binomial theorem coefficients, correct? So that is how you're going to do it. And this formula works for all the values, whether n is positive or negative. So let's be very clear. So in this formula, n belongs to integers for sure. We have tested this so many different ways, and we found that it really works, right? Now here's the last example, slightly different from what we had been doing. We were only testing the coefficients. Now the question for you is, example 4, we'll see the product of negative integers. Prove that the product of 2n consecutive negative integers is divisible by 2n factorial. So you can pause the video, answer this particular question, and then look into my suggestions. Well, since we have 2n factorial, a term here, I thought it's a good idea to work with the number which is positive, because at the end I have to put it in a factorial form, correct? And therefore, we are saying let the negative integer be minus k for a non-negative k, right? So the first statement for me is very important, because now ultimately I want 2k factorial kind of, right? So I want to keep k positive. Since we are working with negative, consecutive negative integers, so we'll say minus k will be my negative integer, correct? And then consecutive is, you can always go with ones, right? So the product of two and negative integers now is what? So it will be definitely, we'll just take away 1 from our integer and keep on doing it, right? So we have to do it how many times? 2n times, correct? So 2n. So it'll be the last term minus 2n plus 1. That is going to be the last term which gets multiplied with minus k, right? So when you include both ends, in that case you have to take away 1 because you added both the ends, correct? So you should be recalling this. How many numbers are between 0 to 9? Well, there are 10 numbers in between, correct? So when you add both the ends, the number of numbers really increases by 1. And so, it is good practice to also check why at times we are always doing something minus 1 at the end. Okay. Perfect. So let's continue with this particular expansion. So again, as our strategy is, we took the minus 1 common. And we know we have 2n of these factors being multiplied. So that power will be 2n. And the series will be as shown. Perfect. So this series is equal to, uh, this is typing, let's forget about this. Okay, so that's the series. Now the product is equal to, now remember, minus 1 to the power of 2n is actually positive 1. So in this case, while going from here to here, we have dropped minus 1 to the power of 2n, correct? So it's kind of dropped. And rest of the things are written here for you. So rest of the things are right there. Now to work out what we have done, so this is same. Okay. What we did was we multiplied and divided by k minus 1 factorial, since we want to complete this factorial list, right? We want to term it in terms of factorials. So we have multiplied both numerator and denominator by k minus 1 factorial. Now that makes a huge difference. We have now in the numerator k plus 2n minus 1 factorial, correct? Because beyond k, we went to k minus 1 factorial, correct? So we got k plus 2n minus 1 factorial right from there. And the denominator, we multiplied. So k minus 1 factorial in the denominator, correct? Now, to get our result, what we did was we multiplied and divided by 2n factorial. Now, when you do that, you can rearrange, taking away 2n on the side, this term, which we're talking about, which is this term, is what? Is this term. K plus 2n minus 1, choose 2n, correct? So that is how you could write this. And therefore, the whole thing boils down to k plus 2n minus 1, choose 2n, times 2n. And that is how we are going to prove that this product of consecutive negative 2n numbers is divisible by 2n. Perfect. So that makes sense. That is how we are going to end this. But I hope you learned in this particular video how we could extend very easily the binomial theorem which we started working with. Initially, we had the condition that both n and r should be integers which are non-negative. And now we can see that the value of n could be a negative integer also, right? And all the formulas which we have learned so far work with minus n also. So that is a very beautiful thing learned. I hope you understand and appreciate it. Feel free to write your comments, share your views, and if you like to subscribe to my videos, that would be great. You can always contact me on my email address for further guidance or visit my website for some exclusive videos on this particular topic. I hope that really helps. Thanks for your time and all the best.